Hi everyone, welcome to Chapter 1 review. I'm going to turn my video off and we'll talk you through the review. Alright, so this is what we covered in the chapter. We covered patterns and sequences, properties of real numbers, algebraic expressions, solvent equations, and solvent inequalities. So we're going to go through each of these and let's take a look at what we did. So if you remember our patterns and sequences, we were looking at what we could add or subtract based on a series of numbers or pictures. So our first example with this 3, 6, 9, 12, and 15 is we want to determine what's so special about the number-to-number run that we have. So we're going to start with the first set, so 3 and 6, and find out what's going on with that. And then we're going to look at 6 and 9 and figure out what's going on with that. And then I'm going to get rid of this little highlight on the bottom. So from 3 to 6, we can say that we're adding 3 or multiplying by 2. And we're just going to carry those two series off to the next set, see if it works the same way that. So 6 to 9, we do increase by 3, but 6 times 2 is 12, so our multiplied by 2 is not an option. So we're going to remove that. And the only thing that we should have left is just that positive 3 that we're seeing each time. Okay, so of course we're going adding 3 each time, so we would say that we're increasing our sequence by 3. And if we were asked to complete the next series of numbers, we could say that it's 18, 21, 24, and so on, depending on what series they're looking for. Now, for the graphics, we kind of do the same thing. We see what's so special about it. So we have 1 block there, we've got 2 blocks there, and we've got 3 blocks there. So I won't insult your intelligence by saying that we're just increasing a block each time. So if we were to draw the 5th one in this series, which would be the next one, all it is 5 blocks in a row. So we also want to keep the pattern that's going on. So if it's in a line, just keep adding pictures in a line. All right, so we also went over tables, and this is where we kind of add a little bit of algebraic expressions to the mix. So on the left we have on the left and right we have function tables, but we're going to focus on the left one right now. And what we're going to look at is starting from the bottom. We're going to see kind of if we can figure out how our y's are increasing. So we want to focus on the y side, and we want to figure out what's going on there. So at the bottom here, we've got 8, and then we go to 6, and then we go to 4, and then we go to 2. So these sound like even numbers, and it looks like they would be a difference of 2 each time. If we would go from 6 to 8, that would be 2, and if we were to go 4 to 6, that would be 2, and if we went from 2 to 4, that would be 2. So it looks like our coefficient that Mrs. Justice helpfully explained to us is going to be 2 in this case, and we have an n, and we don't seem to be, and we can go and check that by looking at number 5. So we should expect number 5 is 10 for the y value, and because we're just adding 2 to 8, and x was just increasing by 1, so let's plug in 5 for x, and this is also going to be our n, so don't get confused by that. And then we're going to put 2 times 5, the number that we're substituting for n in, and see if that's 10. And it is. So that seems like it works. You can go on and try a few other numbers to see if it fits the pattern, but I think we're satisfactorily answering that one. Okay, now moving on to this second set. We're also going to start at the bottom with 4 and 16 and see if we can determine what's going on there and compare it to the one that's going the y value, one that was going on before that. So if I was to just do this and see if there was a an addition property that we can spot, we're going to say from 9 to 16, that increased by 7. From 4 to 9, that increased by 5. And then from 1 to 4, that increased by 3. So there's not much that we can say is special about that addition. Of course, the coefficient's not the same, so I can't just put 5 in here because it was either 3, 5, or 7. So that coefficient is out, and we have to find another way to approach this. So I'm going to erase some of my little tips and helpful hints, and we're going to look at another way of approaching this. So let's start with our x and figure out what's going on with y. So from 4 to 16, what's going on? From 3 to 9, what's going on? And then from 2 to 4, what's going on? And 4 to 16, I could say that is times 4. So 4 times 4 gets me to 16. 3 times 3 gets me to 9. And 2 times 2 gets me to 4. And 1 times 1 gets me to 1. So I've got two of the same number being multiplied together. So I think you might be able to spot that this would be n squared. So any number I put in there, I just multiply it against itself, and that would give me the y value. So if we were to use what we had out here before to find out how much we were increasing, so 3, 5, 7, we could say that our next number should be 9. So 16 plus 9 is 25. So if we wanted to hold with that pattern, we could. Unfortunately, this pattern is not described by squared. So we have to actually plug in a number to see if it works. So 5 for n again, 5 squared, or 5 times 5 is 25. So that would be how we would approach something like that. Okay, properties of real numbers. So we went through kind of like how numbers looked and the different kinds of numbers. And we can start kind of like on our basic system with natural numbers. So natural numbers are our counted numbers, 1, 2, 3, 4, 5. When we start to expand that set, we add in 0, and that includes our whole numbers. So whole numbers are 0, 1, 2, 3, 4, 5. Integers are our natural numbers, but with a negative sign as well. So we expand natural numbers by attaching a negative sign to them, and that covers our integer range. So integers cover the whole number line. So as we draw a number line, we can start at 0, go positive 1, and go negative 1. So that's covered by integers. Rational numbers are simply in the form of a over b. I'm going to change color. So, and I'm going to rewrite my a so it doesn't look like a q. So rational numbers are in the form a over b. So 1 over 2 or 2 over 1, as long as our numbers are different. Of course, this is understood that b is not equal to 0, because if we had b equal to 0, we'd have an undefined number. So that's the only exception in this for rational numbers. And irrational numbers are numbers that we can't give a terminating sequence to. So pi is 3.1415, and it goes on forever with no discernible pattern. The same with the square root of 2. So the square root of 2 is approximately 1.14 and so on and so forth. So don't quote me on that. And it goes on forever with no discernible pattern. So those are irrational numbers. There's nothing rational about them. There's nothing that makes sense about them. They just keep going on and on. So again, we also covered different properties of addition and multiplication. We went through commutative, which is just rearranging the orders of multiplication and addition, and saying that on either side of the equal sign, the order doesn't matter. Associative is similar to commutative. The only issue that we're doing there is addition, is we're rearranging the parentheses. So you can see the parentheses here for a plus b are added first, and then we add c, and on the other side, a is then added to the sum of b plus c. And the answer would be the same on both sides if you plugged in numbers. And that's how we come up with these commutative and associative properties. The same for multiplication. It doesn't matter which order the multiplication is. So it's kind of related to the multiplication commutative addition, but we can have more variables and it doesn't matter what their position is because we're still result in the same answer. And then we have our identities saying that we want to get to the same variable in addition and multiplication. And the way we do that is for addition, we add 0. So anything adding 0 to the number still gives us the number, and then multiplying by 1 for multiplication still gives us the same answer or the same variable. Inverse operations are reciprocals. So the reciprocal of a is negative a for addition, and the reciprocal for multiplication, inverse or reciprocal for multiplication, is 1 over a. So let's see how that actually looks. So we could also say a over 1. Remember that we can say a over b for a rational number, right? And we're going to multiply that by 1 over a. Now, in those cases, the a is going to cancel, and you're going to be left with 1 over 1. And 1 over 1 is just 1, so that's how we get back to our inverse result of 1. Distributive property, all we're doing is taking the outside and multiplying it against both the inside terms. So a times b plus a times c. And in multiplication, it's distribute. In the distributive property for addition and multiplication, it's the same concept. So I take a, multiply it times b, and multiply it times c, and I get ab minus ac. Okay, so moving on to algebraic expressions, we're going to look at this expression, and we're going to evaluate for x equals 2. Instead of just plugging in the 2 for x, we might want to simplify this first and run through a simplification process to just make our steps easier. So we're going to, it may make it easier. So actually, you know what? I hope I don't confuse you guys, but I'm going to do it. I'm going to do both. So if I plugged in, if I simplified, so I'm going to say simplify x. And if I said, I'm just going to plug in 2. This is going to give, we'll start with the plug in 2 first. So 1/3, 3 times 2 minus 6 minus 3 minus 2x. Sometimes this will not work, but this gave me a nice idea that this might actually work out with not too much issue. So I'm sorry, I forgot to multiply by 2. All right, so we'll work inside this first left set first. So 6 minus 6 minus, and we'll carry on 3 minus 4. Okay, so 1/3, do the parentheses first, and I come up with 0, and minus 3 minus 4, which is negative 1. So 1/3 times 0 is 0, and then minus 1 is plus 1. So we end up with 1 for for our answer. Now, in simplification, sorry for the sound. So we're going to distribute this 1/3 into the parentheses. So 1/3 of 3x is just going to give me x, and 1/3 of 6 is going to be 2. And all I'm doing is putting a coefficient on top of that, and also putting 6 on top of the 6/3. So 6 divided by 3 is 2, and that's where that came from. Okay, and then I'm going to subtract my 3 minus 2x. All right, so now we're going to distribute this -1 throughout the second set of parentheses. So I'm going to keep the x minus 2, and now I'm going to distribute and take away the parentheses as I go. So -1 times 3 is going to give me -3, and a -1 multiplied a -2x is going to be give me plus 2x. Now I'm going to drop the parentheses on everything, and I'm going to combine like terms. So x plus 2x minus 2 minus 3, and combine them, so that's 3x minus 5. And I have to go plug 2 back in. So 3 times 2 is 6 minus 5, and that equals 1. So we came to the same result. A little bit more steps in the simplification process. We were lucky that in the second set, when we were just dropping in a 2 in this, we came out with a 0 in the first parentheses. So that's kind of why I spotted that and decided that I might want to show you that as well. Okay, now we want to simplify. So this is all about combining like terms, and we kind of did that in the last slide. The only issue with this one is that we're adding an exponent into the mix. So we have to combine like exponents. So in this case, I'm going to write out 5r squared and plus 5r squared just to keep them together, and then minus the r. So these two will add together nicely to 10r squared, and then we just minus the r. And that's this is a simple case for simplification, but all you're doing is just going through combining stuff that has the same exponent and moving on. Okay, solving equations. So this time what we're going to do is solve for x in this case. So we say in this equation that both sides are equal, so we have to find a number in x that is equal. That will give us 49 on both sides. Okay, so here we go. We're going to distribute the 3 into the parentheses. So 3, one more time, 3 times 2x plus 3 times 4 equals 49. 6x plus 12 equals 49. And now we have to balance by taking the constant out and leaving the variable x on by itself. The way we get the plus 12 out of there is to subtract the inverse operation of addition. So we subtract 12 from both sides, and we get 6x equals 37. And now we have to do the same thing with our multiplication, and our inverse operation is going to be division. So we divide by 6 to clear out that x. And we don't have to reduce, or we can't reduce that fraction into anything simpler. So we're just going to keep the 37/6. And you don't have to turn that into a mixed number. So in this case, when we're solving equations, we just leave the fraction in the simplest form, which is, or as the improper fraction in that case, so it's 37/6. Okay, so the process of solving equations. If you remember the last slide, we said that the 49 has to equal in some way, the term on the left. And so equations should always be true. And there are cases where it's not, especially if you're doing a data analysis and you're trying to put together a whole bunch, a data set, and trying to come up with a solution to a problem. Some data sets will never give you the solution you're looking for, and you have to be careful that that what you write out is going to be true. So we're going to spot how an equation is always true or never true, and they're sometimes true as well, but we're just going to focus on these two since the sometimes is in the middle, and you'll be able to spot those as well. So always true. We're going to just put, when we try and figure this out, we're going to get all our x's on one side and all our constants on another side. And we're going to see how that sorts out. So 4x minus 4x, because I have to remove the 4x from this side, is equal to 5 minus 5, which is removing the 5 from this side. So I skipped a couple of steps. Hopefully you see it, and if not, complain to me and I'll. So 4x minus 4x gives me 0x, and 5 minus 5 is 0. So the good thing is that no matter what number I plug in for x in this case, I have to multiply it by 0. Anything multiplied by 0 is going to be 0. So 0 equals 0. And in that case, that's true. So this equation works. If I was to plug in numbers for it and just use an example, 4 times 1 plus 5 equals 5. 4 times 1. I could say that this is going to be 9, and that's going to be equal to 9, and you see that this worked. And of course, for always true, you're going to have, it's going to take a little bit more numbers to actually go and prove that, but as a check, this seemed to work. All right, never true. So we're going to balance our equation by getting the x's on one side and constants on the other. So 3x minus 3x equals 4 minus 2, and then we have 0x equals 2, and again, any number that I plug in for x, I'm going to get 0 on the left hand side, and I'm going to have 2 on the right hand side. So does 0 equal 2? It does not. So in this case, this equation is never going to be true, and we could verify that by again plugging in 1 or any other number that we wanted for x to verify and seeing what our solution is. So 3 plus 2 equals 3 plus 4, 5 equals 7, and no, it does not. So that's how we look at whether an equation is true or not true. Okay, and if you remember, we did solving inequalities. We're going to solve and graph. So let's go through this real quick. 3x minus 1. All right, I'll start over again. I'm going to subtract 1 from both sides, and I'll get 3x on one side and 6 on the other. I'm going to divide by 3, and I'm going to get x is less than 2. So when I graph that, make my number line, start with 0. I don't have to start with 0 all the time. I can any number on the number line to kind of get us started, but and then we're going to say, because it's less than 2, we want to open circle, and then we just want to go to the left because every number less than 2, and just signify that I'm going to the left of my number line. Okay, so here is the next slide. We're going to divide by 2, and we're going to have x less than 2, or on this side, we're going to have, so divide by 3 to get the x by itself. X is greater than or equal to 3. And then we're going to do our graph. And I'm going to start with 0 on my left-hand side. And I'm going to go 1, 2, 3, 4. And x less than 2, open circle on the 2. Fill in everything to the left. And x is greater than or equal to 3, so I'm going to have a closed circle, and I'm going to fill in everything to the right of 3. So the only situation where x cannot equal either of these equations is at 2 and in between 2 and 3. So here is where our x's not be able to match either equation. Or inequality, I should say. Okay, so next slide.